There is something out there that should not exist. Not in the way we casually say that about a strange creature, or an unusual weather pattern, or a coincidence so improbable it makes you laugh. No, this is different. This is something that, according to the foundational laws that govern every atom, every force, every breath of energy in this universe, should be physically, mathematically, and cosmologically impossible. And yet, it is there. It has been measured. It has been photographed. It has been confirmed by independent teams of scientists working in separate countries, using separate instruments, operating under entirely separate assumptions. And what they all found, what they all had to sit down and reckon with in the quiet of their labs and offices and sleepless nights, was the same impossible thing. Something that should not exist, does exist, and nobody, not a single human being alive on this planet right now, can fully explain why. You might be tempted to brush that off. You've probably heard dramatic claims before. Science channels love to tease you with mysteries that turn out to have clean explanations by the end of the video. A strange signal from space that was actually a pulsar, an anomalous particle reading that was instrument error, a bizarre observation that was explained away by some elegant equation scrawled on a whiteboard. You've been disappointed before. You've been led to the edge of something vast and mysterious only to find that the view was smaller than advertised. But I need you to understand, before we go any further, that this is not one of those times. What you are about to encounter is not a mystery that science has quietly solved while you weren't looking. This is a mystery that is actively breaking scientists' minds right now, today, as you sit here and watch this. The people who study it go home at night and stare at the ceiling. And so before I tell you what it is, I want you to take a breath. Because the way you understand reality is about to become slightly less stable than it was a minute ago. To understand why this thing is so disturbing, you first have to understand what science actually is at its most fundamental level. Science is not just a collection of facts about the world. It is a system of expectation. It is a language of prediction. When a physicist says that something should or should not exist, they are not expressing a personal opinion or a cultural bias. They are saying that the mathematical framework we have built over centuries of observation, experimentation, and refinement points unambiguously in one direction. They are saying that when you follow the logic of the universe from its established starting points, you arrive at a specific answer, and that answer does not include the thing they just found. That gap between the prediction and the reality, that's where this story lives. That gap is where everything gets uncomfortable. Think about the nature of scientific law for a moment. When Isaac Newton described gravity in the 17th century, he wasn't guessing. He was encoding something real, something observable, something that could be used to predict the motion of planets with extraordinary precision. When James Clerk Maxwell unified electricity and magnetism in the 19th century, he didn't just describe what he had seen. He predicted the existence of electromagnetic waves, and Heinrich Hertz found them exactly where Maxwell said they would be. When Albert Einstein proposed that space and time are not fixed and absolute but woven together into a single fabric that can bend and stretch, it sounded like philosophy. It sounded like madness. And then astronomers pointed their telescopes at the right part of the sky during a solar eclipse in 1919 and saw starlight bending exactly as Einstein had predicted. The laws of physics are not suggestions. They are the deepest grammar of the universe. The rules by which everything that has ever happened has happened, and the rules by which everything that will ever happen will happen. Or so we thought. Here is what makes a scientific law so powerful and so psychologically important. It has never been wrong in the domain where it applies. Not once. Thermodynamics has never been observed to fail in a closed system. The speed of light has never been clocked faster than itself in a vacuum. The conservation of energy has never been violated in a laboratory. These are not merely successful theories. They are the bedrock of our understanding, the load-bearing walls of the entire structure of human knowledge about the cosmos. And when something appears that violates one of them, when the data comes back and the numbers refuse to fit, when the anomaly doesn't go away after you've checked everything 3 times and replaced the instruments and recalculated from scratch, what you're left with is not just a scientific puzzle. You are left with a crack in the foundation. And cracks in foundations don't stay small. Let's start with the thing that started all of this. Let's start with the object that, when it was first discovered, made a group of experienced astronomers go completely quiet, in a way that people who work in science almost never go quiet. These are people who are trained to be skeptical, people who have spent their careers explaining away anomalies, people who default to the most boring possible explanation for any given data point, because the most boring explanation is almost always the right one. But this time, when the data came back, When the numbers were verified and the measurements were cross-referenced and the instruments were checked for error, not a single one of them could reach for the boring explanation. Because the boring explanation didn't exist. The object they were looking at, the thing sitting there in the data, quiet and patient and utterly impossible, had no boring explanation. It had no explanation at all. You need to understand something about how the universe is supposed to age. The cosmos has a history, and that history moves in one direction. The universe began approximately 8 billion years ago in an event we call the Big Bang. Though that name is slightly misleading because it wasn't really an explosion in the conventional sense, and there was no empty space for it to explode into. What it was, at the deepest level we can describe, was the emergence of space, time, energy, and matter from a state of unimaginable density and temperature. In the earliest moments after the Big Bang, the universe was a seething, opaque plasma of particles so energetic that they couldn't even form atoms. Then, as space expanded and things cooled, protons and electrons combined to form hydrogen and helium. The universe became transparent. The first light traveled freely through space for the first time, and then, over hundreds of millions of years, gravity did its slow, patient work. Gas collapsed into clouds. Clouds collapsed into stars. Stars burned and died and exploded, seeding the cosmos with heavier elements, and from those elements more complex structures formed. Galaxies, galaxy clusters, the vast cosmic web that spans the observable universe. This is a process that takes time, a very specific, well-understood amount of time. The critical point here is that the early universe was supposed to be simple, hot, dense, rapidly expanding, but fundamentally simple in its structure. The complex things, the massive galaxies, the enormous black holes, the sprawling clusters of stars, those things require time to form. You can't build a skyscraper before you've quarried the stone and cut the lumber and poured the foundation. The laws of physics, as we understand them, dictate a very clear timeline for how complexity emerges from simplicity. You need hundreds of millions of years before the first stars ignite. You need billions of years before galaxies reach the kind of scale and structure we see in the nearby universe. The math is not ambiguous about this. The models are not vague. The timeline for cosmic evolution is one of the most robustly tested and precisely calibrated predictions in all of astrophysics. And then the James Webb Space Telescope turned its golden mirrors toward the farthest reaches of the observable universe, and it found something that had no right to be there. When astronomers pointed the James Webb Space Telescope at the deep field, at a tiny patch of sky that looks essentially empty to the naked eye, a patch you could cover with a grain of sand held at arm's length, they expected to see what the Hubble Space Telescope had shown them when it did the same thing decades earlier but in greater detail. They expected to see small, young, chaotic galaxies in the early universe. Galaxies that looked like the universe they were supposed to inhabit. Raw, unsettled, still forming, because the universe at that age had simply not had enough time to produce anything more refined. That was the prediction. That was what the models said. That was what the laws of physics demanded. What they actually found was something profoundly different. They found galaxies, enormous, mature, structurally complex galaxies, sitting in an era of the universe where, by every established understanding of cosmology, they could not possibly have had time to form. These galaxies were too big, too old, too developed. They looked like galaxies that should exist in the relatively nearby universe, the universe of today or thereabouts. But they were sitting in the universe as it existed just a few 100 million years after the Big Bang. And that should be impossible. To feel the weight of what that means, imagine you are an archaeologist. You've spent your career digging through layers of earth, and you understand perfectly well what you should find at each depth. Pottery shards and simple tools in the shallow layers, stone arrowheads and primitive shelters deeper down. And at the very deepest levels, the levels that represent the earliest human presence in a region, you expect the most rudimentary evidence of existence, basic fire pits, rough stones, the earliest tentative scratches of a species just beginning to organize itself. And then one day, at the deepest level in the layer that represents the very earliest habitation, you find a fully constructed iron bridge. Not a hint of one, not a fragment, a complete, complex engineered structure that should not be possible for another 10,000 years of technological development. That is approximately the level of wrongness we are talking about when astronomers look at these galaxies and then look at when they exist in cosmic time. The specific objects that caused the most immediate alarm were described in a series of papers published by researchers working with JWST data beginning in 2022. These were not marginal findings tucked into footnotes. They were headline results that immediately sent ripples through the astrophysics community. One study identified 6 massive galaxies existing at a redshift corresponding to roughly 500 to 700 million years after the Big Bang. To put that in context, the universe is 13.8 billion years old. These galaxies were spotted when the universe was less than 5% of its current age. And yet, according to the analysis, some of them contained as many stars as the Milky Way contains today. The Milky Way, our home galaxy, took approximately 13 billion years to accumulate its stellar population. These galaxies appeared to have done something comparable in a fraction of that time. Joel Leja, one of the astronomers involved in the analysis, put it in terms that were unusually stark for a scientific publication. He said that finding these objects was like finding an adult human in the fossil record, from a time when only single-celled life was supposed to exist. The metaphor is not an exaggeration. It is a precise description of the structural contradiction. You might be thinking, okay, but science makes mistakes. Instruments miscalibrate. Redshift measurements can be tricky. Maybe the distance estimates are wrong. And yes, that was absolutely the first thing the scientists themselves thought, because scientists are professionally paranoid about exactly those kinds of errors. They rechecked the redshift measurements. They used multiple independent methods to estimate distances. They cross-referenced with other telescopes and other data sets. They had colleagues run the same analysis with different software, and the results held. The galaxies were where the data said they were, in the time period the data indicated with the stellar masses the models calculated. The error bars, the margins of uncertainty that are built into every scientific measurement, were not large enough to explain the discrepancy. Not even close. The objects were real, they were distant, they were early, and they were enormous. And there was no existing model of cosmology that could account for all of those facts simultaneously. But here's where it gets even stranger, because the JWST galaxies are not the only thing that shouldn't exist. They are just the most recent and most visible entry in a list that has been quietly growing for decades. A list that, when you lay all the items out side by side and look at them together, stops feeling like a collection of isolated anomalies and starts feeling like something else entirely. It starts feeling like a pattern. And patterns, when they point away from your expectations with enough consistency, stop being anomalies and start being evidence of something you don't understand yet. The JWST galaxies are a doorway, but the room on the other side of that doorway is much larger and much darker than a single telescope finding. Let's go back further, not in cosmic time, but in the history of scientific confusion. Because the universe has been sending us signals it shouldn't be sending for a very long time, and we have been doing our best to ignore them, or explain them away, or quarantine them in the corners of journals where fewer people will feel unsettled by them. One of the oldest and most persistently disturbing of these signals is what cosmologists call the Hubble tension. The Hubble tension sounds like the name of a legal drama, but it is in fact one of the most important and unresolved crises in modern physics. To understand it, you need to understand what the Hubble constant is, and why disagreeing about its value matters more than you might initially think. Edwin Hubble, the man, not the telescope, was the first person to demonstrate conclusively that the universe is expanding. In the 1920s, he measured the distances to what were then called nebulae, fuzzy patches of light in the night sky, and he found that the farther away they were, the faster they appeared to be moving away from us. This relationship between distance and recession velocity became known as Hubble's law, and the constant that describes that relationship, the ratio of recession speed to distance, became known as the Hubble constant. It is usually written as h0, and it is measured in units of kilometers per second per megaparsec, which is a way of saying, for every 3.26 million light-years of distance, a galaxy moves away from us by this many kilometers per second. The value of the Hubble constant is one of the most fundamental numbers in cosmology. It tells you how fast the universe is expanding right now, and from that you can work backward to determine how old the universe is, how large the observable universe is, and how all of the structures within it have evolved over time. It is, in a very literal sense, the heartbeat rate of the cosmos. The problem is that there are two completely independent ways to measure the Hubble constant, and they give different answers, not slightly different, not within the margin of experimental error, genuinely, significantly, unambiguously different. The first method uses the cosmic microwave background, the faint glow of light left over from the early universe, the afterglow of the Big Bang itself. When scientists analyze the patterns in that ancient light, patterns that encode information about the physical conditions of the universe when it was only 380,000 years old. They get a value for the Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. The second method uses a different approach, measuring the distances to nearby galaxies using a carefully calibrated chain of distance indicators, Cepheid variable stars, type Ia supernovae, and other cosmic measuring sticks, and then measuring how fast those galaxies are moving away from us. When you do it that way, you get a value of approximately 73 to 74 kilometers per second per megaparsec. The difference between those two numbers is around 9%. And 9% might not sound like much, but in the context of physics, where our measurements are supposed to agree to within fractions of a percent, 9% is an earthquake. For many years, scientists hoped that the disagreement was due to some systematic error, a miscalibration in one of the measurement chains, a subtle bias in the way the data was being processed, some overlooked source of noise. These are the kinds of explanations that scientists reach for instinctively, because they are the kinds of explanations that have resolved previous discrepancies. But as the measurements have become more precise, as the instruments have improved and the datasets have grown larger, the tension has not gone away. It has grown. The measurements have gotten more accurate, and the discrepancy between them has gotten more significant, not less. As of the most recent analyses, the statistical significance of the Hubble tension is above 5 sigma, which is the threshold that physicists use to declare a detection real rather than a statistical fluke. In other words, the probability that the disagreement is due to random chance is less than 1 in a million. This is not a rounding error. This is not instrument noise. Something is genuinely wrong, and nobody agrees on what it is. What could explain the Hubble tension? The possibilities range from the mundane to the extraordinary, and none of them are comfortable. One class of explanations suggests that there is new physics happening in the early universe, some unknown form of energy or particle that briefly altered the expansion rate before fading away, skewing the measurements derived from the cosmic microwave background. Another class of explanations suggests that our distance measurements in the local universe are systematically biased in some way, that the Cepheid stars we use as cosmic rulers are not as reliable as we thought. But every time researchers go looking for these systematic errors and failing to find them, the more radical possibility becomes slightly harder to avoid, that our model of the universe, the standard cosmological model known as lambda CDM, which has been one of the great triumphs of modern science, is fundamentally incomplete, that the universe is not behaving the way our best theories say it should. And if that's true, then what else is it doing that we don't know about? To feel how unsettling the Hubble tension really is, consider what it would mean for the universe if the two measurements are both correct. If the universe is expanding at 73 kilometers per second per megaparsec as measured locally, but only at 67 is measured from the early universe, then something must have happened between the early universe and now to cause the expansion to speed up in a way that our models don't predict. Something accelerated the universe beyond what the standard model says should have happened. You might be thinking, but wait, don't we already know the universe is accelerating? Don't we have dark energy for that? And yes, we do. The discovery that the expansion of the universe is accelerating was announced in 1998 and earned its discoverers the Nobel Prize in 2011. But here's the thing, dark energy as it is currently modeled is not supposed to produce the level of additional acceleration needed to explain the Hubble tension. Dark energy, in the standard model, is a smooth, constant energy density that fills all of space uniformly and pushes everything apart at a steady rate. It is not supposed to have changed over time in the way that resolving the Hubble tension would require. So either dark energy is not what we think it is, or something else entirely is responsible for the discrepancy. Both of those possibilities are alarming in different ways. And then there is dark matter itself, which is perhaps the most philosophically strange thing that mainstream science has ever been forced to accept. Dark matter is not a fringe idea. It is not a speculation on the margins of physics. It is embedded into the standard cosmological model. It is factored into every serious calculation about how galaxies form and move and evolve. Astronomers have spent decades mapping its distribution through the universe using a technique called gravitational lensing, watching the way the gravity of invisible mass bends the light of distant objects in ways that only make sense if there is something there that we cannot see. And the evidence for dark matter is overwhelming. not in the sense that we have detected any dark matter particles directly, but in the sense that the universe's behavior makes no sense without it. Stars in the outer regions of galaxies orbit far too fast. They should fly apart if the only gravitational influence on them was the visible matter we can see. Something invisible must be holding them in. The math is unambiguous. About 27% of the universe's total energy density is made up of dark matter, and yet in more than 50 years of searching, using some of the most sensitive detectors ever built, buried deep underground in former mines to shield them from interference, we have not found a single dark matter particle. Not one, not even a hint of one. The Large Underground Xenon Detector in South Dakota, the Xenon 1T experiment at the Gran Sasso Laboratory in Italy, the Panda-X experiment in China. These are just a few of the massive, exquisitely sensitive instruments that have been searching for the most popular candidate for dark matter, a class of particles called weakly interacting massive particles, or WIMPs, for decades. The idea behind WIMPs was elegant and appealing. They would interact with ordinary matter only through gravity and the weak nuclear force, making them effectively invisible to most instruments but detectable in principle through very rare interactions with atomic nuclei. The detectors were built, the experiments ran, the data came back, and the silence was deafening. WIMPs, at the masses and interaction strengths that cosmological models suggested they should have, are not there. Or if they are hiding so effectively that they might as well not be. Each new generation of detectors has pushed the sensitivity further and come back empty-handed, and with each negative result, the most straightforward versions of WIMP dark matter become less plausible. We know dark matter is there because the universe moves as if it's there. We just cannot find it in any direct sense, and the gap between knowing something exists and being able to find any direct evidence of it is a gap that science normally closes over time. This gap is only getting wider. Here's what that gap should make you feel. You are standing in a room. The room has furniture in it. You know the furniture is there because you keep bumping into it in the dark. The universe keeps behaving as if the furniture is there. But every time you turn on the light, the room appears empty. And not because the light is bad. The lights have been getting better and better, more powerful, more precise, covering a wider and wider range of frequencies. And still, nothing. Just the empty room and the certainty, derived from your bruised shins and displaced center of gravity, that something is there that you cannot see. Now imagine that the furniture makes up 27% of everything in the room. That is where dark matter stands right now. But wait, because there's something even more disturbing layered on top of the dark matter problem. Something that takes the concept of invisible and unknowable and elevates it into a different category altogether. Dark energy, not dark matter, dark energy. They sound similar, but they are conceptually quite different. And dark energy is, in the considered opinion of many physicists, the most bizarre thing that science has ever been forced to accept as real. Dark energy is the name we give to whatever is causing the accelerating expansion of the universe. We know something is causing it. The evidence is as solid as physics gets. When astronomers measure the distances to type Ia supernovae, which are stellar explosions that always produce approximately the same intrinsic brightness and can therefore be used as standardized candles to measure cosmic distances, they found that the supernovae in the distant universe are farther away than they should be if the universe were expanding at a constant rate or slowing down due to gravity. This meant that the expansion was speeding up, and the only way to make that happen, within the framework of general relativity, is to introduce a form of energy that permeates all of space and exerts a negative pressure, a kind of repulsive force built into the fabric of space-time itself. Dark energy, in the current model, accounts for approximately 68% of the total energy density of the universe. Combined with dark matter's 27%, that means that everything we have ever seen, every star, every galaxy, every planet, every atom, every person, every instrument we have ever built, everything that responds to our measurements and fills our data and represents our entire scientific understanding of the physical world, all of that accounts for approximately 5% of what exists. 5%. The universe is 95% something else. Something we cannot directly detect, cannot identify, cannot explain from first principles, and cannot reproduce in any laboratory. We have given it names: dark matter, dark energy. But giving something a name is not the same as understanding it. We understand the name, we don't understand the thing. And when you think about what this means for the foundations of science, for the system of expectation and prediction we discussed at the beginning, the discomfort sharpens considerably, because science's greatest achievement has always been the idea that the physical world in principle is knowable, that with the right instruments, the right mathematics, and the right conceptual framework, we can understand the nature of reality in its entirety. We can peel back every layer. We can illuminate every shadow. We can bring every mysterious phenomenon into the light of understanding. Dark matter and dark energy are a direct challenge to that belief. They are not just unsolved problems. Every era of science has unsolved problems. They are a suggestion that 95% of the universe operates by rules we have not discovered, and possibly by rules that are fundamentally different from the ones we have discovered. They are a suggestion that our map of reality, however detailed and intricate, covers only a tiny fraction of the actual territory. Now let's descend into the quantum world, because if the cosmological scale has been quietly dismantling our certainty, the quantum scale has been actively assaulting it for nearly a century, and the wounds have never fully healed. Quantum mechanics is perhaps the most successful physical theory ever developed. Its predictions match experimental results to a precision that is genuinely astonishing, in some cases to more than 10 decimal places. When Richard Feynman described quantum electrodynamics, the quantum theory of electromagnetic interactions, he compared its accuracy to measuring the distance from New York to Los Angeles to within the width of a human hair. It works. It works extraordinarily well, and yet at the same time, nearly everyone who has ever thought carefully about what quantum mechanics actually says about the nature of reality has come away disturbed in some way that is difficult to articulate clearly and impossible to fully resolve. The disturbance starts with a concept called superposition. In quantum mechanics, a particle, an electron say, or a photon, does not have definite properties before it is measured. It exists in a superposition of multiple possible states simultaneously. An electron can be spinning clockwise and counterclockwise at the same time, until the moment you measure it, at which point it abruptly and apparently randomly settles into one or the other. This sounds strange enough in the abstract, but the strangeness is not just philosophical, it is experimentally verified. The famous double-slit experiment, in which individual particles are sent through two narrow slits to land on a screen, demonstrates this in a way that is almost physically repulsive to the intuition. When you send electrons through the two slits without measuring which slit they go through, they create an interference pattern on the screen, the pattern of overlapping waves. This can only happen if each individual electron passes through both slits simultaneously, interfering with itself. When you add a detector to measure which slit the electron goes through, the interference pattern disappears, and you get what you'd expect from particles: two bands, one behind each slit. The act of measurement, of gathering information, changes the physical outcome. The universe behaves differently when it is being watched than when it is not. This is not a metaphor. This is not a loose analogy. This is a precise, quantitative, reproducible experimental result that has been confirmed thousands of times by hundreds of independent laboratories. The universe, at the quantum level, does not have a definite state until something interacts with it and forces it to declare one. Before that interaction, it exists in a genuine superposition of all possible states, each with a certain probability, and the act of measurement collapses that superposition into one definite outcome. This is called the measurement problem, and it is one of the most persistently unresolved foundational questions in all of physics. Because if the act of measurement causes the superposition to collapse, then what counts as a measurement? Does it require a conscious observer? Does it happen whenever a quantum system interacts with a larger classical system? Is there a physical process that causes collapse, or is collapse just a change in our knowledge? Physicists have been arguing about this since the 1920s, and there is still no consensus. And the argument is not a minor technical dispute. It is a disagreement about the nature of reality itself, about whether the universe has a definite state independent of observation, or whether observation is somehow constitutive of reality. But the measurement problem, as disturbing as it is only the beginning of quantum mechanics' assault on common sense. The thing that reaches deeper, the thing that bothered Einstein so much that he spent the last decades of his life trying to prove it wrong and failed, is entanglement. Quantum entanglement is the phenomenon whereby two particles that have interacted can become correlated in such a way that the state of one particle instantly determines the state of the other, regardless of the distance between them. If you measure one particle of an entangled pair and find that it is spinning clockwise, you instantaneously know that its partner is spinning counterclockwise, even if that partner is on the other side of the galaxy. And this correlation is not the result of the particles carrying some hidden information that was set at the moment they interacted. It is not as if they were pre-programmed with their outcomes before you measured them. A series of experiments, beginning with those performed by Alain Aspect in 1982, and extending through increasingly sophisticated tests up to and including loophole-free Bell tests in 2015 and beyond, have demonstrated conclusively that entanglement cannot be explained by any local hidden variable theory. The correlations are real, they are instantaneous across any distance, and they cannot be explained by anything that travels between the particles. This is not a theoretical possibility, it is an observed fact, and it directly violates our most basic intuition about how causality and locality work, about how one thing can influence another, only if something physical passes between them. Einstein called entanglement spooky action at a distance, and he meant it dismissively. He was convinced that quantum mechanics was incomplete, that there must be some deeper underlying theory that would restore locality and determinism to the universe. He proposed, with Boris Podolsky and Nathan Rosen, a thought experiment designed to show that quantum mechanics led to an absurd conclusion, the EPR paradox, which argued that either the quantum description of reality was incomplete, or that two particles could instantly influence each other across any distance, which seemed to violate relativity. Einstein was certain the first option must be true. John Bell later turned the paradox into a testable prediction, and the experiment showed that Einstein was wrong. The universe really is non-local in the quantum sense. Two particles, no matter how far apart, can share a connection that allows their properties to be correlated in ways that nothing in classical physics can explain. And this is not a small, edge case, rarely encountered phenomenon. Entanglement is everywhere. Every quantum interaction can produce it. The atoms in your body right now are entangled with particles scattered across the cosmos as a result of interactions that happened before you were born. The universe is, at the deepest level, a web of non-local connections, and the implications of that are still being worked out. One of the most haunting implications of entanglement is what it does to our concept of space. If two particles can be correlated instantaneously across any distance, if there is some sense in which they remain connected regardless of how far apart they are, then what does distance actually mean? We experience space as a fundamental property of reality. Objects are separated by space, and nothing can cross that space faster than light. But entanglement seems to suggest that for certain types of physical correlations, space doesn't matter. That the distance between two entangled particles is in some sense irrelevant to the connection they share. Some physicists have taken this very seriously and proposed that space itself, the three-dimensional arena in which we experience everything, is not fundamental. That it is an emergent property, something that arises from a deeper layer of reality in which the concept of spatial separation doesn't exist. Juan Maldacena and Mark van Ramsdonk, working in the field of string theory and quantum gravity, have proposed that the geometry of space is literally encoded in patterns of quantum entanglement, that the fabric of space-time and the web of quantum connections are different descriptions of the same thing. If that's true, then space is not the container in which everything exists. It is itself a consequence of something more fundamental. And if space is not fundamental, then our entire intuitive picture of reality, objects existing in definite locations, separated by definite distances, influencing each other only through local interactions, is not just incomplete, it is a simplification, a useful fiction, a shadow on the wall of a deeper cave. We are still at the quantum level, and there is more. There is the matter of virtual particles, which are one of the strangest concepts in all of physics, and which have been experimentally confirmed to be real, which makes them strange in a very precise and uncomfortable way. Virtual particles arise from the Heisenberg uncertainty principle, specifically from the version of it that applies to energy and time. The uncertainty principle, in its most famous form, says that you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. But there is a second, equally important version. You cannot simultaneously know both the energy of a system and the time over which you're measuring it with perfect precision. This means that the energy of empty space, and of a vacuum, is not perfectly defined. It fluctuates. Pairs of particles spontaneously pop into existence out of nothing, exist for an incredibly brief moment, and then annihilate each other. This is not a theoretical curiosity. It is a physical reality, and we can measure it. The Casimir effect is one of the most direct demonstrations that the quantum vacuum is not empty, but seething with virtual particle activity. If you take two very smooth uncharged metal plates and place them incredibly close together in a vacuum, we're talking distances of nanometers, they experience a small but measurable attractive force. There is nothing between them, no particles, no fields, no air, and yet they are drawn together. The explanation is that the virtual particles that fill the vacuum between the plates are restricted to wavelengths that fit between the plates, while the virtual particles outside the plates can have any wavelength. This creates a slight imbalance in the radiation pressure on either side of each plate, and that imbalance manifests as a force. The Casimir effect has been measured to high precision, and it matches the quantum mechanical prediction beautifully. Empty space pushes things together. Nothing is exerting a real measurable force. If that doesn't make you feel slightly unsteady, read it again. But the Casimir effect, while strange, is manageable. What is considerably less manageable is what happens when you try to calculate the total energy density of the quantum vacuum, the total energy of all those virtual particle fluctuations per unit volume of empty space, and compare it to the observed energy density of the universe. When you do that calculation, using the best available theory of quantum fields, you get a number, and then you compare that number to the observed value of dark energy, the energy density of the vacuum that we infer from the accelerating expansion of the universe, and the two numbers disagree, not by a factor of 2, not by a factor of 10, not by a factor of 100. They disagree by a factor of approximately 10 to the power of 120. That is one followed by 120 zeros. In the history of physics, in the entire body of quantitative science, there is no other case where a theoretical prediction and an observed measurement have disagreed so spectacularly, by so many orders of magnitude. Richard Feynman himself called it the worst theoretical prediction in all of history. And the reason it is so devastating is not just the size of the discrepancy, it is what the discrepancy suggests about our theories. If the quantum vacuum energy were as large as quantum field theory predicts it should be, the universe would not look anything like it does. A vacuum energy density, 1 to 120 times larger than what we observe, would generate a repulsive force so overwhelmingly powerful that space would expand at a rate so ferocious that no atom could ever hold itself together, no star could ever ignite, no galaxy could ever coalesce, no planet could ever form, no chemistry could ever happen. The universe would be a formless, violently expanding void of raw energy, spread so thin so fast that complexity of any kind would be permanently and absolutely impossible. The universe we actually live in, with its stars and galaxies and chemistry and biology and consciousness, should not exist under those conditions, and yet it does. Which means either the vacuum energy is somehow being canceled out, almost perfectly, by some other contribution we don't understand, or our theory of the quantum vacuum is deeply, fundamentally wrong. Both possibilities are catastrophic for our sense of theoretical completeness. Both possibilities say that something enormous is missing from our understanding of how the universe works at its most basic level. And the uncomfortable truth is that we do not know which possibility is correct, and we do not have a convincing candidate for what the missing piece might be. This problem has a name. Physicists call it the cosmological constant problem, and it has been described as the greatest unsolved problem in theoretical physics. The cosmological constant is the term in Einstein's equations of general relativity that represents the energy density of empty space, and Einstein actually introduced it in 1917 for reasons that had nothing to do with quantum mechanics. He used it to make his equations describe a static universe, which was the prevailing cosmological assumption at the time. When Hubble showed that the universe was expanding, Einstein famously called the cosmological constant his greatest blunder and removed it. Then, in 1998, when the accelerating expansion of the universe was discovered, the cosmological constant was brought back because it was the simplest mathematical way to account for dark energy. And now it sits at the center of a crisis. Quantum field theory predicts a value for it that is 120 times too large, and nobody has any fully satisfying explanation for why the actual value is so incredibly, almost suspiciously small. Not zero, which would at least be explainable by some symmetry, but just barely not zero. Vanishingly small, but not vanishing. Precisely tuned, apparently, to a value that allows the universe to exist in a form capable of hosting complexity. And that word, tuned, opens a door that many physicists are reluctant to walk through, but which keeps swinging open on its own. The door leads to what physicists call the fine-tuning problem, and it is one of the most philosophically loaded topics in all of science. The laws of physics contain a number of fundamental constants, numbers like the strength of gravity, the mass of the electron, the charge of the proton, the speed of light, the cosmological constant, and these constants have very specific values. What is extraordinary, And what has been noted repeatedly by physicists and cosmologists over the past several decades is that if those values were even slightly different, the universe would be radically inhospitable to complexity of any kind. Change the strength of the strong nuclear force by a few percent, and either protons can't bind together to form nuclei at all, or everything fuses into helium immediately after the Big Bang and there's no hydrogen left to make stars. Change the ratio of the electromagnetic force to gravity by a small amount, and stars either burn so fast they exhaust their fuel in millions of years rather than billions, not long enough for planets to develop life, or they burn so slowly and dimly that the energy output is insufficient to drive the chemistry of life. Change the cosmological constant by even a tiny fraction of the absurd value that quantum mechanics predicts, and either the universe collapses back on itself almost immediately, or it expands so fast that matter never condenses into structures. The universe we have, the one capable of producing you and your ability to sit here and contemplate these things, exists because a set of numbers are tuned to values that seem almost perversely well suited to producing it. This observation, which is sometimes called the anthropic coincidence or the fine-tuning of the universe, is real, and it is quantitative, and it is not going away. The question it raises is whether the fine-tuning is an illusion, a selection effect, a physical necessity, or something else entirely. Some physicists argue that the constants are not actually independent, that a deeper theory, a theory of everything, will show that they are all related to each other in ways we don't yet understand, and that their values are not arbitrary but required by some deeper mathematical structure. If that's true, the fine-tuning is not fine-tuning at all. It is inevitability wearing the costume of contingency. Other physicists invoke the multiverse, the idea that there are an enormous, possibly infinite number of universes, each with different values for the fundamental constants, and that we necessarily find ourselves in one of the universes that allows for our existence, because we couldn't find ourselves in any other kind. The fine-tuning is then explained not by any special status of our universe, but by the fact that observers can only exist in universes where the conditions permit observers to exist. And still other physicists are uncomfortable with both of those explanations and are searching for a third path, one that doesn't require either a mathematical miracle or an infinite ensemble of unobservable universes. But none of them have found it yet, and in the meantime, the numbers sit there, precisely calibrated to allow you to exist, with no explanation for why. There is another piece of this that needs to be placed carefully on the table because it connects the quantum world to the cosmological world in a way that amplifies the strangeness of both. It is the question of what happened at the very beginning. At the moment of the Big Bang, or more precisely in the first fractions of a second after whatever it was that gave rise to the universe, the physical conditions were so extreme that neither general relativity nor quantum mechanics can adequately describe them. General relativity is the theory of the very large, gravity, space-time curvature, the large-scale structure of the cosmos. Quantum mechanics is the theory of the very small, particles, fields, probability, superposition, and in the conditions of the early universe, both regimes apply simultaneously. Everything is simultaneously incredibly dense, so dense that quantum effects are crucial, and incredibly energetic, so that the curvature of space-time is extreme, and we don't have a theory that can handle both at once. We don't have a theory of quantum gravity. We have candidates, string theory, loop quantum gravity, causal dynamical triangulations, and others, but none of them is complete. None of them makes unique and testable predictions that have been verified, and none of them commands the kind of universal acceptance that general relativity and quantum mechanics individually enjoy. The universe, at the moment of its birth, is precisely the conditions under which our physics breaks down entirely. We literally cannot describe what happened at the beginning of everything. Our best theories go up to a certain point, a moment called the Planck time, approximately 10 to 43 seconds after the Big Bang, and then they stop working. What happened before that, or what the singularity at the Big Bang actually means physically, is a question our mathematics cannot currently answer, and this is where a particular kind of vertigo begins to set in. Because you might have come into this video with a mental image of science as a vast, mostly complete structure, with a few interesting gaps still to be filled in, the kind of picture that popular science writing often presents, with physics as 95% finished and just waiting on a few final details to be worked out. But what we have been describing is not a few final details. We have been describing a situation in which the entirety of what we can see and measure and understand, every atom, every star, every galaxy, every quantum interaction, every observation ever made, constitutes 5% of what exists. We have been describing a situation in which our two greatest physical theories, general relativity and quantum mechanics, are mutually inconsistent and cannot both be correct as they stand. We have been describing fundamental constants that are tuned to life-permitting values by mechanisms we don't understand. We have been describing a vacuum that should be radiating energy 120 times more powerfully than it does. We have been describing a universe that is expanding faster than our models predict. And we have been describing ancient, massive galaxies that appeared too early, too fully formed, in defiance of our best cosmological models. These are not gaps in our knowledge. These are chasms, and the chasms are not in the places we expected them to be. Let's dwell for a moment on the galaxy problem, specifically because the JWST discoveries are still unfolding, and what has been found since those first alarming papers went public has not reduced the alarm. It has increased it. As more data has been processed, as more distant galaxies have been identified and characterized, the anomalous pattern has become more robust, not less. Researchers have found not just large, star-rich galaxies in the early universe, but also evidence for what appear to be supermassive black holes, the kind of colossal gravitational singularities that sit at the centers of mature galaxies, existing in that same impossibly early epoch. Supermassive black holes are among the most extreme structures in the universe, containing millions or billions of times the mass of the Sun within a region smaller than the solar system. We don't fully understand how they form even in the modern universe, in the 13-billion-year-old cosmos where they have had all the time in the world. But in the early universe, just a few 100 million years after the Big Bang, they should be essentially non-existent. And yet JWST has found signatures consistent with them at those redshifts. Objects so massive, so structurally complex, so developmentally advanced for their cosmic age, that the lead researchers on these projects have used phrases in their published papers that scientists almost never use. Challenges our current understanding, may require new physics, inconsistent with standard formation scenarios. These are not the words of excitement at a new discovery within an existing framework. These are the words of people staring at something that shouldn't be there. One specific finding deserves particular attention because it crystallizes the problem with unusual clarity. In early 2023, a team of researchers announced the discovery of a galaxy they designated JD's GS Z13-0, which existed when the universe was only approximately 320 million years old, a universe that was just about 2% of its current age. To exist at that redshift with the properties it displayed, this galaxy had to have formed its stars and accumulated its mass with a speed that defies any conventional formation model. The models that govern how gas collapses into stars, how stellar feedback from supernovae and radiation regulates star formation, how galaxy structure develops over time. None of these models, when run forward from the initial conditions of the early universe, can produce what was observed. It's not a matter of tweaking a parameter here or there. The object simply should not be there at that time in the way it is there. And yet there it is, sitting in the data, measured, confirmed, written up in peer-reviewed journals, presenting itself to our instruments with a kind of calm indifference to our inability to explain it. The scientists working on these findings are in an interesting and psychologically unusual position. They are not the first scientists in history to face an anomaly that their models couldn't explain. That has happened throughout the history of science, and usually the resolution has been found within a reasonable time frame. But the character of these anomalies feels different to many of the people involved. When an anomaly is found at the edge of a theory's domain of validity, when it's in a regime the theory was never designed to handle, the anomaly doesn't feel threatening to the foundations. It feels like an invitation to extend the theory. But when an anomaly appears in the middle of the theory's domain, where the theory should be working perfectly, that's when the unease deepens. The JWST findings are not from a regime where cosmological models are untested. They are from a regime that the models were specifically designed to address, and the models are failing. This is not theory at its edge. This is theory at its core, and the core is cracking. There is a question that gets asked in physics departments, not always out loud, not always in formal contexts, but in conversations over coffee, and in the silent moments when a researcher is alone with their data and their thoughts. The question is, what if the problem is not the theory? What if the problem is the framework? What if the issue is not that we need a better version of our current models, better parameters, more precise measurements, additional terms in the equations, but that we are building on a foundation that is itself subtly wrong? What if the conceptual categories we use to describe the universe, the very language in which we ask our questions, is not adequate to the answers the universe is giving us. This is a more radical suggestion than it might initially appear, because science has always assumed that even when individual theories fail, the methodology that generates and tests them is sound. But what if the universe is operating by a logic that our cognitive architecture is not well equipped to grasp? What if we are in a position analogous to trying to describe a symphony using only a vocabulary of shapes and colors? We might be able to capture something real, but we would be missing most of it, and worse, we might not even know how much we were missing. This brings us to something that is rarely discussed in popular science content, but is taken seriously by a significant number of physicists and philosophers of science. The possibility that certain features of physical reality are, in principle, not fully accessible to human cognition and perception. We know intellectually that our perceptual apparatus evolved to help us survive on the surface of a planet at a particular scale, at particular velocities, in an environment where quantum effects are completely negligible and gravitational effects are manageable. Our brains did not evolve to intuitively grasp phenomena that operate at the Planck scale, or at cosmic scales of billions of light years, or at velocities approaching the speed of light, or in conditions of extreme space-time curvature. We can do the mathematics, and the mathematics can guide our understanding far beyond the intuitive, but there is a question of whether the mathematics itself, which is after all a product of human cognition, can reach every corner of physical reality. Whether there are features of the universe that are simply outside the space of things that minds like ours can form adequate representations of. The philosopher Thomas Nagel once wrote about what it is like to be a bat, his point being that the subjective experience of echolocation is not just unknown to us, but in principle unimaginable, because we lack the sensory apparatus to anchor any genuine understanding of it. We can describe echolocation mathematically, we can measure its frequency and range, we can study the neural processing that underlies it, and none of that will give us the first-person experience of moving through space by constructing a three-dimensional model of the world from reflected sound. Now extend that intuition to the universe itself. What if certain fundamental features of physical reality are, to minds like ours, as inaccessible as echolocation is to a creature with no auditory system? What if there are aspects of how the cosmos actually works that our mathematical tools can gesture toward, can describe the effects of, but cannot truly penetrate? This is not mysticism. It is a sober recognition that cognitive systems have inherent limitations, and that there is no particular reason to believe that human cognition, even augmented by mathematics and instruments, is sufficient to understand everything there is to understand about the universe. But let's not retreat too quickly into the philosophical, because there are specific physical phenomena that make this concern feel less abstract and more immediate. One of them is the black hole information paradox, which has been one of the most hotly contested questions in theoretical physics for the past 50 years and remains unresolved. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where the curvature of space-time becomes infinite and our equations break down completely. The boundary of the region from which escape is impossible is called the event horizon, and the question that Stephen Hawking raised in the 1970s, which has haunted physics ever since, is this: what happens to information when it falls into a black hole? In quantum mechanics, information is sacred. The laws of quantum mechanics are time-reversible and unitary, which means that in principle, if you know the exact quantum state of a system at any moment, you can calculate its quantum state at any other moment, forward or backward in time. Information is never created or destroyed, it is only rearranged. This is not a philosophical preference, it is a mathematical requirement of the theory, but black holes seem to violate it. When matter falls into a black hole, all of the specific quantum information it carries, the precise quantum states of all its constituent particles, appears to vanish behind the event horizon, inaccessible to the outside universe forever. Hawking showed in 1974, using a semi-classical calculation that combined quantum mechanics and general relativity, that black holes are not actually perfectly black. They emit a faint radiation due to quantum effects near the event horizon, a radiation that has come to be called Hawking radiation. Eventually, over an astronomically long timescale, a black hole will radiate away all of its mass and evaporate completely. And here is the problem. Hawking showed that this radiation is perfectly thermal. It is pure randomness, encoding no specific information about what fell in. So when the black hole evaporates, all of the information about the matter that formed it and fell into it is gone, destroyed, erased from the universe. This is called the black hole information paradox, and it represents a direct, irresolvable conflict between general relativity and quantum mechanics as currently formulated. If Hawking is right, then information is destroyed in black holes, and quantum mechanics is violated. If quantum mechanics is right, then information must somehow survive. But nobody can convincingly explain how, because general relativity says that the inside of a black hole is causally disconnected from the outside. The two theories cannot both be correct. One of them, or perhaps both of them, must be modified in some fundamental way to resolve the paradox. Physicists have proposed many solutions. The information is somehow encoded in the Hawking radiation in a subtle, non-thermal way. The information is stored in a remnant left behind after the black hole evaporates. The information is released at the end of evaporation in a final burst. Space-time has a microstructure at the Planck scale that provides an escape route for information, but none of these solutions is fully satisfying, and none has been demonstrated to actually work in a mathematically rigorous way. The paradox stands. The conflict between our two greatest theories, embodied in the question of what happens to information in a black hole, remains one of the deepest unresolved tensions in all of physics. The implications of the information paradox extend beyond black holes themselves, because if information can be destroyed, then the universe is fundamentally non-deterministic in a way that goes beyond the familiar randomness of quantum mechanics. Not just unpredictable in detail, but in principle non-reversible. The past does not fully determine the future, and the future does not fully determine the past. The arrow of time becomes not just a thermodynamic tendency, but a fundamental feature of reality, and the universe at its deepest level is not a closed, information-conserving system, but something more like a leaky vessel, losing content over time. Alternatively, if information is preserved, which most physicists, leaning on the principle of unitarity, believe must be the case, then general relativity must be wrong in a way that is not yet understood, and the event horizon of a black hole must work differently than Einstein's equations say it does. Either way, something we thought we knew is wrong. Either quantum mechanics has a flaw at the level of its most fundamental principles, or general relativity has a flaw in one of its most basic predictions, and we don't know which. Now take a step back. You have been accumulating these anomalies, these contradictions, these places where the universe refuses to behave the way our physics says it should. The impossible early galaxies, the Hubble tension, the undetectable dark matter, the inexplicable smallness of dark energy compared to the quantum prediction, the fine-tuning of fundamental constants, the measurement problem in quantum mechanics, the non-locality of entanglement, the breakdown of physics at the Planck scale, the black hole information paradox. You might still be filing these away as separate problems, isolated puzzles that will eventually each get their own solution. But consider the possibility, and this is a possibility that an increasing number of serious physicists are entertaining, that they are not separate, that they are all symptoms of the same underlying disease, that the universe is, again and again, in domain after domain, at scale after scale, doing something that our framework cannot account for, and that this repetition is not coincidence, that it is the universe's way of telling us that something is wrong with the map, not just the territory. There is a phrase that gets used in physics, usually with a mixture of excitement and dread: new physics. When an experiment returns a result that cannot be accommodated by existing theories, physicists say it might be pointing to new physics, some deeper or more comprehensive understanding that extends beyond what we currently know. New physics is exciting because it means we are about to learn something genuinely unprecedented, but it is also frightening, in a quiet, intellectual way, because every time we invoke new physics, we are admitting that the universe has something that our accumulated centuries of understanding have failed to capture. We are admitting that the conversation between human minds and physical reality is not as far along as we thought. And when the number of places where new physics is needed accumulates to the extent it has accumulated in the early 21st century, the framing shifts slightly. It's no longer just exciting, it's disquieting. It suggests not that we're on the verge of the next chapter of physics, but that we may be at the beginning of a much longer and more difficult story than we imagined. Let's talk about something specific that has been quietly generating unease among physicists for the past decade or so: the results from the Large Hadron Collider. The LHC, the Great Particle Accelerator built by CERN beneath the border of France and Switzerland, is the largest and most energetic particle collider ever constructed. It was designed in part to probe the physics beyond the standard model of particle physics, the theoretical framework that describes all known elementary particles and 3 of the 4 fundamental forces. The standard model is enormously successful. It predicted the existence of the Higgs boson decades before it was found, and the Higgs was duly discovered at the LHC in 2012. That discovery was a triumph of the scientific method, a confirmation of a 48-year-old prediction that required extraordinary experimental effort to test. But the discovery of the Higgs, while celebrated, was also, in a sense, the beginning of a new kind of anxiety. Because the standard model, while extremely successful, has problems. It doesn't include gravity. It doesn't explain dark matter. It doesn't explain why the Higgs boson has the mass it does, rather than the much higher mass that quantum corrections suggest it should have, a problem called the hierarchy problem. And the most popular solutions to these problems, developed over decades of theoretical work, predicted that the LHC would find something beyond the Higgs. New particles, new symmetries, new forces. The most popular and theoretically motivated of these extensions was called supersymmetry. Supersymmetry is a theoretical framework that posits a deep symmetry between 2 fundamental classes of particles, fermions, which make up matter, and bosons, which carry forces, such that every fermion has a corresponding superpartner boson, and every boson has a corresponding superpartner fermion. Supersymmetry solves the hierarchy problem elegantly. It provides a natural candidate for dark matter in the form of the lightest superpartner particle, and it has beautiful mathematical properties that make it extremely appealing theoretically. For decades, supersymmetry was the leading candidate for the new physics beyond the standard model, and many physicists expected that when the LHC reached sufficient energy, superpartner particles would start appearing in the data. The theoretical predictions varied, but there was broad consensus that if supersymmetry was correct in a form that solved the hierarchy problem, superpartners should be accessible at LHC energies, and the LHC looked. It looked carefully, extensively, with exquisite sensitivity, across a huge range of energy and particle type combinations, and it found nothing. No superpartners, no new particles of any kind beyond the Higgs. The data came back clean, in the way that a crime scene that has been thoroughly wiped is clean. Perfectly, suspiciously, disturbingly clean. The absence of supersymmetry at LHC energies does not definitively rule out supersymmetry. It could exist at higher energies, and some theorists have retreated to versions of the theory in which the superpartners are heavier and therefore not yet accessible. But the original, most natural, most theoretically motivated versions of supersymmetry, the ones that solve the problems they were invented to solve without introducing additional fine-tuning, those versions are now deeply constrained, if not outright ruled out. And the broader point is that the LHC, which was expected to open a new era of discovery and reveal the physics beyond the standard model, has come back with one discovery, the Higgs boson, and then essentially silence. The desert beyond the standard model, which theorists had hoped would turn out to be a garden, appears at the energies the LHC can probe to actually be a desert, and that silence is information. It is telling us that something is wrong with our theoretical expectations, that the extensions of the standard model we were most confident in were pointing in the wrong direction, that the universe, again, is not doing what we expected, that the most successful theory of fundamental particles in history has a boundary beyond which we cannot yet see, and we do not know what lies on the other side. This brings us to something that has been lurking at the edges of this conversation, something that is no longer confined to the fringe, but has begun to appear in serious theoretical physics literature, something that more and more physicists are willing to at least consider as a logical possibility, even if it makes them uncomfortable to say so out loud. The possibility that the universe is, in some meaningful sense, not what it appears to be. Not in the trivial sense of quantum mechanics telling us that particles don't have definite properties before measurement, and not in the slightly less trivial sense of general relativity telling us that space and time are dynamical and curved. In a deeper sense, the possibility that the physical world as we experience it, the three-dimensional space, the flow of time, the solidity of matter, the local causal structure, is a kind of emergent representation, a surface phenomenon arising from a deeper substrate that operates by entirely different rules. And the most provocative specific version of this idea, the one that has attracted the most attention and generated the most controversy, is the simulation hypothesis. The simulation hypothesis, as it is usually presented in popular culture, is a speculative philosophical idea that the universe might be a computational simulation run by some sufficiently advanced intelligence. Nick Bostrom formalized a version of it in 2003 in a paper called "Are You Living in a Computer Simulation?", in which he argued that at least one of three propositions must be true. Either virtually all civilizations at our level of development go extinct before reaching the computational capability to run detailed reality simulations, or virtually all civilizations that do reach that capability choose not to run such simulations, or we are almost certainly living in a simulation. The logic is probabilistic and depends on assumptions about the development of civilizations and the nature of consciousness, and it has been critiqued extensively. But what is interesting is not so much the Bostrom version, which is largely philosophical and unfalsifiable as stated, but the degree to which serious physicists working on fundamental questions about the nature of reality have started to arrive at structurally similar conclusions from entirely different directions. Consider the holographic principle. This is not a speculative idea. It is a well-established result in theoretical physics, arising from the study of black holes and string theory. The holographic principle states that all of the information needed to describe the physics within a volume of space can be encoded on the surface area bounding that volume. In the same way that a two-dimensional hologram can contain all the information needed to reconstruct a three-dimensional image, the three-dimensional physics inside a region of space can be fully described by a two-dimensional theory on the boundary. This was first suggested by Gerard 't Hooft and Leonard Susskind in the early 1990s, and it was given a specific and mathematically precise realization by Juan Maldacena in 1997 in what is now known as the ADS-CFT correspondence. In this framework, a theory of gravity in a three-dimensional space plus time is exactly dual to a quantum field theory with no gravity, living on the two-dimensional boundary of that space. The three-dimensional volume, with all its physics and structure, is a holographic projection of the two-dimensional boundary. The implications of the holographic principle are worth sitting with for a moment because they are genuinely strange in a way that has nothing to do with speculation. If the holographic principle is correct, then the three-dimensional world we experience, the world of depth and volume and spatial extension, is not the fundamental level of reality. It is a derived representation of something that exists on a lower dimensional surface. Our three-dimensional world is, in a mathematically precise sense, a projection, not a metaphorical projection, not a loose analogy, but a literal encoding of information onto a lower dimensional structure. The depth of the world around you, the distance between you and the wall across the room, the height of the sky above you, the three-dimensional structure of everything you can see and touch, that depth may not be fundamental. It may be an emergent property of the way information is organized on a boundary that you will never be able to see or touch or interact with directly. If that is true, then what is fundamental is not the three-dimensional world of our experience, but something radically different, something encoded on a surface, something for which our entire intuitive picture of reality, our experience of living in a three-dimensional space filled with three-dimensional objects, is not even approximately accurate. It is a useful representation, the way a flat map is a useful representation of a spherical Earth, but the map is not the territory, and in this case, the difference between the map and the territory is not just in the details, but in the number of dimensions. There is a related and equally disorienting development in theoretical physics that goes by the name of the ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. ER refers to Einstein-Rosen bridges, as what are commonly called wormholes, which are solutions to Einstein's equations that connect two distant points in space-time through a kind of shortcut, a tunnel through the geometry of space. EPR refers to the Einstein-Podolsky-Rosen paper, the 1935 thought experiment about quantum entanglement. The conjecture is that these two phenomena, which seem to belong to completely different domains of physics, are actually the same thing, that every pair of entangled particles is connected by a microscopic Einstein-Rosen bridge, a wormhole. That quantum entanglement and geometric connectivity in space-time are not just analogous or related but identical, that the fabric of space-time, the spatial connections between different regions of the universe, is literally built from quantum entanglement. Every entangled pair of particles sews together two regions of space with a thread of geometric connection. The more entanglement, the stronger the geometric connection. Space itself, the arena in which all of physics happens, is a structure woven from quantum correlations. If ER-EPR is correct, then quantum mechanics and gravity are not just compatible, They are different faces of the same coin. The non-locality of quantum entanglement and the geometry of space-time are not two separate features of reality that need to be reconciled with each other. They are the same feature, seen from two different angles. Space is not a background stage on which quantum events play out. Space is the outcome of quantum events. The fabric of reality is not a container for quantum information. It is constituted by quantum information. And if that is true, if space-time emerges from quantum entanglement, then the deepest level of physical reality is not spatial at all. It is informational. It is a network of quantum correlations, of entangled relationships between degrees of freedom, and the spatial world we experience is a kind of large-scale, coarse-grained representation of that informational network, the way temperature is a large-scale representation of the average kinetic energy of molecules. Real, useful, a good description for most purposes, but not fundamental, not the deepest truth. You might be feeling by now a certain kind of disorientation, a loosening of the moorings that normally keep your sense of reality stable and manageable. That feeling is appropriate. It is the correct emotional response to the information, because what we have been describing, piece by piece, is a systematic undermining of the most basic assumptions about what the world is. We started with galaxies that shouldn't exist and ended up at the possibility that space itself doesn't exist in the way we think it does. We went from a measurement disagreement in the Hubble constant to the possibility that our entire cosmological framework is built on an incomplete foundation. We went from missing dark matter to missing 95% of everything. We went from quantum weirdness at the scale of individual particles to a conception of reality in which the entire three-dimensional universe is a holographic projection from a lower-dimensional informational substrate, and at each step, the anomalies were not invented or exaggerated. They were real, measured, confirmed, and peer-reviewed. The disorientation is not the product of excessive speculation. It is the appropriate reaction to an honest accounting of where the science actually stands. Let's go back to the beginning of the universe one more time, because there is something there that deserves more attention, something that connects to everything else we've been discussing and adds another layer to the strangeness. It is the problem of cosmic inflation and why the universe looks the way it does on the largest scales. When you look at the cosmic microwave background, the ancient light left over from the Big Bang, you find something remarkable. The temperature of the CMB is almost perfectly uniform across the entire sky. Whether you look in one direction or the opposite direction, at regions of the sky that are separated by billions of light years in the modern universe, and were separated by enormous distances in the early universe, the temperature is the same to within 1 part in 100,000. This is called the horizon problem. The two regions of sky have never been in causal contact with each other. No signal traveling at or below the speed of light could have traveled between them in the time available, and yet they have the same temperature. How did they coordinate? How did they come to equilibrium with each other if they were never in contact? The standard answer to the horizon problem is cosmic inflation, a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, during which the universe expanded by a factor of at least 10^26 in a time shorter than 10^32 seconds. During inflation, regions that were in causal contact before inflation, that had equilibrated with each other, were stretched to cosmic scales, which is why they share the same temperature today. Inflation also smooths out any spatial curvature, explaining why the universe appears geometrically flat to high precision, and it provides the mechanism for generating the tiny quantum fluctuations in the density of the early universe that, amplified by gravity over billions of years, grew into the cosmic web of galaxies and voids we see today. Inflation is in many ways a beautiful theory. It solves multiple problems simultaneously and makes testable predictions that have been confirmed. But it also has a problem, a very significant problem. We have no idea what caused it. We don't know what the inflaton, the field responsible for driving inflation, actually is, where it came from, or why it stopped. Inflation is, in a sense, a description of what must have happened rather than an explanation of why it happened. It is a placeholder for understanding, a mathematical framework that correctly describes the universe's early behavior without providing any deep physical account of the mechanism behind it. And the deeper you look into the theory of inflation, the more troubling it becomes. One of the most disturbing aspects of inflation is what happens when you take the theory seriously and follow its implications all the way to their logical conclusion. Most models of inflation predict that once inflation starts, it doesn't just stop everywhere at once. In different regions of the inflating space, quantum fluctuations cause inflation to end at different times. In some regions, inflation ends quickly, and a universe like ours forms. In other regions, inflation continues, and those regions expand exponentially, becoming larger and larger, generating more and more space. And within that expanding space, new regions where inflation ends and new universes form, and other regions where inflation continues further. This process, called eternal inflation, never stops. Once started, it generates an infinite number of pocket universes, each potentially with different physical properties, different values for the fundamental constants, different laws of physics. Our universe, on this picture, is one bubble in an infinite, eternally inflating sea of universes, separated from each other by expanding inflationary regions that can never be crossed. The multiverse is not just a philosophical speculation in this context. It is a direct prediction of the most successful model of the early universe we have, and it is a prediction that is, in any direct sense, completely untestable. The other bubble universes are beyond any possible observational horizon, forever inaccessible, their existence a matter of theoretical inference rather than empirical evidence. The multiverse creates a deep problem for the scientific method, because the scientific method is built on the principle of empirical testability. A theory that predicts things that cannot, even in principle, be observed or measured or tested is not fully scientific in the traditional sense. It is more like a mathematical framework with philosophical implications. Some physicists are comfortable with this, arguing that the multiverse is a logical implication of theories that are well tested in other domains, and that we should accept it as a theoretical inference even without direct observational confirmation. Others are deeply uncomfortable, arguing that a theory that cannot be tested is not physics but metaphysics, and that the popularity of the multiverse idea represents a troubling departure from the empirical foundations of science. This debate is not just an internal argument about methodology. It reflects a genuine uncertainty about whether the universe is the kind of thing that human science, as currently practiced, can fully understand, whether the deepest truths about reality are accessible to observation and experiment, or whether some of them live permanently beyond any horizon we can reach. And here the story takes a turn that I want you to feel, not just understand. Because we have been building up a case, presenting anomaly after anomaly, contradiction after contradiction, gap after gap, and you might be expecting that we are approaching some kind of synthesis, some grand unified theory of why everything is wrong, some explanatory framework that will make all the pieces fit together. I need to tell you clearly that we are not approaching that. There is no synthesis. There is no resolution waiting at the end of this. What we are approaching is something different. The recognition that the accumulation of anomalies and contradictions is itself the deepest finding. That the pattern of failure is the message. That the universe is not merely hiding a few secrets from us, while otherwise cooperating with our investigation. It is doing something that starts to feel, when you examine it with the appropriate seriousness, like systematic non-cooperation, like a puzzle that keeps gaining pieces faster than they can be assembled, like a door that opens onto another door, and another, with no room ever revealed. Only the suggestion of rooms beyond rooms beyond rooms. Let's talk about time, because time is something that everyone experiences directly and intimately, more intimately in some ways than space. You feel the passage of time in your body, in your memory, in the aging of the world around you. And yet time, when examined carefully, turns out to be one of the most mysterious and poorly understood features of physical reality. The laws of physics, at the fundamental level, are almost entirely time-symmetric. Newton's equations work the same if you reverse the direction of time. The equations of electromagnetism work the same in both temporal directions. Quantum mechanics works the same forward and backward. General relativity works the same in both temporal directions. Even the laws of thermodynamics, which give rise to the arrow of time through the concept of entropy, are themselves time-symmetric at the microscopic level. The appearance of an arrow of time emerges from statistical behavior of large numbers of particles, not from any fundamental asymmetry in the microscopic laws. And yet time, as we experience it, flows in one direction only. The past is fixed, the future is open, and the present moment is the moving boundary between them. Memory works in one direction. Causation works in one direction. We age. We cannot unage. Things break and do not spontaneously reassemble. Ice melts in a warm drink and does not spontaneously refreeze. These features of our experience are so fundamental that it is almost impossible to imagine reality without them. And yet they are not present in the fundamental laws of physics. The standard explanation for the arrow of time, proposed by Ludwig Boltzmann in the 19th century, and elaborated by many physicists since, is that the universe started in an extremely low entropy state, an extremely ordered, improbable configuration, and has been evolving toward higher entropy, more disordered states ever since. The arrow of time is just the direction of increasing entropy, and the reason entropy increases in one direction and not the other is the low entropy initial condition of the Big Bang. But this explanation, while widely accepted, only pushes the mystery back one level. Why did the universe start in such an extraordinarily low entropy state? The probability of the early universe having the precise, smooth, ordered configuration it had, purely by chance, is almost incomprehensibly small. Some calculations suggest it is on the order of 1 in 10 raised to the power of 10, raised to the power of 123, an initial condition that specific does not arise by chance. It must have been imposed somehow or selected for somehow, or it represents something about the nature of the Big Bang that we do not yet understand. The arrow of time, the most viscerally real feature of our experience, depends on an initial condition that cannot currently be explained. The fundamental direction of causation, the fact that the past determines the future and not the other way around, rests on a foundation we cannot account for. There is a physicist named Sean Carroll who has written and spoken extensively about the problem of time, and he makes a point that is worth dwelling on. He notes that the question, why did the universe start in a low entropy state, is one of the most important unanswered questions in all of physics, and that it is also one of the most ignored, because it is so difficult and so fundamental that most physicists prefer to take it as a given and move on. The initial condition of the universe is treated as a boundary condition, something you plug into your equations rather than something you derive from them. But taking the initial condition as given is, in a deep sense, admitting that we don't understand why the universe is the way it is at the most basic level. We don't understand why time has a direction. We don't understand why causation flows the way it flows. We don't understand why the past is different from the future. We experience these things with complete certainty in our daily lives, and we have absolutely no fundamental theoretical account of them. The most immediate feature of our existence, the fact that we are embedded in a flowing present, moving from a fixed past toward an open future, is something that our deepest physics cannot explain. Now layer on top of that the implications of quantum mechanics for the nature of time. In the standard formulation of quantum mechanics, there is a time parameter, but it is treated as a classical background, a fixed, absolute parameter against which quantum events are described. This is philosophically inconsistent with general relativity, in which time is not a fixed background but a dynamical feature of spacetime, one that can be curved and stretched and dilated by gravity and motion. When you try to combine quantum mechanics and general relativity into a theory of quantum gravity, you run into a peculiar result known as the Wheeler-DeWitt equation. The Wheeler-DeWitt equation is the quantum mechanical version of the Einstein field equations. It is the equation that describes the quantum state of the universe as a whole, and in the Wheeler-DeWitt equation, time does not appear at all. The equation is completely timeless. There is no time variable in it. The quantum state of the universe does not evolve with respect to time, because in the full quantum gravity context, there is no external time for it to evolve with respect to. Time, in the most fundamental description of the universe we can currently write down, simply does not exist. What we experience as time, the flowing, directional, causally ordered succession of moments, is, in the quantum gravity picture, an emergent phenomenon. It arises at large scales, in situations where quantum gravity effects are negligible, as a kind of effective parameter that describes changes in the relationships between physical degrees of freedom. Time is not a fundamental feature of the universe. It is something that emerges like temperature from molecular motion, like sound from pressure waves, like the solidity of a table from the interactions of atoms. The flow of time, the thing that makes your life feel like a story rather than a frozen tableau, is not basic to the universe. It is a derived quantity, a macroscopic illusion generated by the behavior of a large quantum system, real and important at the scale of human experience but absent from the deepest level of physical description. And if that is true, then the universe at its most fundamental level is not a story. It is something static, timeless, a fixed quantum state from which the appearance of change and causation and history emerges as a large-scale approximation. The narrative of the universe, the Big Bang, the evolution of stars and galaxies, the emergence of life, the moment you are living right now, is not the fundamental reality. It is the shadow of a reality that has no time in it at all. You should feel at this point a particular quality of unease that is different from the unease of not knowing an answer to a specific question. This is the unease of suspecting that the questions themselves might be formulated wrongly, that the framework in which we ask, why does the universe expand the way it does, and where does dark matter come from, and how did those galaxies form so quickly, might be a framework that is not adequate to the depth of what we are asking about, that we are in some sense using the wrong language, not just missing some vocabulary words but operating with a grammatical structure, a syntax of concepts that is too coarse to capture what is actually happening. And this suspicion is not the conclusion of people who have given up on understanding. It is the conclusion of people who have understood so much, so deeply, that they have arrived at the limits of what the current understanding can contain. The greatest physicists of the past century, Einstein, Bohr, Heisenberg, Feynman, Dirac, were not modest about what they had achieved, and they had enormous confidence in the power of mathematical physics to penetrate the nature of reality. And yet all of them at different points expressed deep uncertainty and unease about whether the foundations of their theories were correct, whether the conceptual framework was adequate, whether they were truly understanding or merely describing. If the people who built the house were uncertain whether the foundations were sound, what should we, who merely live in it, feel? Let's talk about something that has been surfacing more and more in the conversations of physicists who work at the foundations of the field. Something that is connected to everything we have discussed, but that adds a specifically human dimension to the mystery. It is the question of consciousness, not in the mystical or unscientific sense, but in a very precise and troubling sense that arises directly from the most basic interpretational questions about quantum mechanics. We mentioned earlier that in quantum mechanics, the act of measurement, of observation, causes the superposition of a quantum system to collapse into a definite state. We mentioned that this raises the question of what counts as a measurement, and we noted that in some interpretations of quantum mechanics, particularly in the original Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, the role of the observer is essential. The quantum wave function on this view is not a description of the physical state of a system independent of observation, but a description of what an observer can know about a system, and observation in this context requires a conscious observer. The collapse of the wave function, the moment at which quantum potentiality becomes classical actuality, is in some versions of quantum mechanics tied to consciousness in a way that has never been fully formalized and has never been fully eliminated. John von Neumann, one of the greatest mathematicians of the 20th century, analyzed the quantum measurement process in rigorous mathematical terms and concluded that within the framework of quantum mechanics as standardly formulated, there is no point in the physical chain of interactions, from the quantum system to the detector to the amplifier to the readout device to the scientist's eyes, where the collapse can be unambiguously located. Every step in the chain is itself a quantum system, and every step can be described by the Schrödinger equation, which does not produce collapse. The only point at which something outside the Schrödinger equation enters is the conscious observer. Wigner's friend, a thought experiment devised by the physicist Eugene Wigner, illustrates this with uncomfortable clarity. If a quantum measurement is performed inside a sealed lab by Wigner's friend, and Wigner waits outside, then from the inside perspective, the measurement has been made and the wave function has collapsed. But from Wigner's outside perspective, the entire system, the lab, the equipment, the friend, is in a superposition until Wigner himself makes an observation. This is logically inconsistent unless consciousness plays a special role in the collapse, or unless the concept of the wave function has collapsed means something different from different perspectives. Either way, the result is deeply strange. Most physicists today are uncomfortable with giving consciousness any special role in quantum mechanics, and the majority favor interpretations that avoid it. The many worlds interpretation, in which the wave function never collapses but all outcomes occur in branching parallel histories, or decoherence-based approaches that explain the apparent collapse as the result of quantum systems becoming entangled with their environments in ways that suppress interference effects. But none of these interpretations is fully satisfying, and none has become universal. The many worlds interpretation avoids the problem of consciousness at the cost of positing an infinite proliferation of parallel realities. each as real as the one you experience, with no way to select which branch you will find yourself in after a measurement. Decoherence explains why quantum effects become invisible at macroscopic scales without fully explaining why only one outcome is experienced. The measurement problem in its deepest form has not been solved. It has been rephrased and managed and quarantined. And at the heart of every version of the problem, if you push deep enough, you find a question that science does not currently know how to answer. What is the relationship between physical processes and subjective experience? What is the relationship between the equations that describe the universe and the fact that there is someone in the universe to whom things feel like something? This question, the relationship between matter and mind, between physical process and subjective experience, is what David Chalmers has called the hard problem of consciousness. The easy problems of consciousness are understanding how the brain processes information, integrates signals from different sensory systems, generates behavior, stores memories, produces speech. These are hard in the practical sense. They involve extraordinarily complex neuroscience and cognitive science, but they are not hard in principle. Given enough understanding of the brain and its computational processes, we could in principle explain all of these functions mechanistically. But even if we had a complete mechanistic account of all of those functions, there would still remain a question unanswered. Why does all that processing feel like something? Why is there a subjective experience associated with seeing red or tasting sweetness or feeling grief? Why isn't all that neural processing just processing, happening in the dark, without any inner light of experience? This is not a question about neural correlates or functional mechanisms. It is a question about why there is any experience at all. And it is a question that our current scientific framework has no principled way to approach. The hard problem of consciousness is not just difficult, it is, in its current form, completely intractable by any method we have. And here is where the pieces start to connect in a way that is either deeply illuminating or deeply terrifying, depending on your temperament. If consciousness cannot be explained by the physical processes of the brain, or if the explanation requires some fundamental expansion of our physical framework, then the relationship between mind and matter is not what materialist science assumes it to be. The standard scientific worldview holds that consciousness is a product of the brain, a high-level emergent phenomenon of sufficiently complex information processing. On this view, there is nothing mysterious about consciousness in principle. It is just very complicated chemistry and computation, and the reason it feels special is because it is our experience of our own processing, seen from the inside rather than the outside. But this view has never been able to bridge the explanatory gap between the physical description, neurons firing, ions flowing, action potentials propagating, and the fact that any of it is experienced. The physical description is complete as a description of mechanism. It is completely silent on the question of experience. And some physicists and philosophers have begun to wonder whether this silence is permanent, whether the physical framework as currently constructed is simply unable to account for consciousness. Not because we haven't finished the job, but because the framework doesn't have the resources to do the job. Some researchers have proposed that the solution requires extending physics itself, adding to our physical framework new fundamental properties or laws that deal with consciousness directly, rather than trying to derive consciousness from physical properties that have nothing to do with it. The most developed version of this proposal is called panpsychism in philosophy and integrated information theory in neuroscience and physics. The idea, associated with Giulio Tononi and others, that consciousness is a fundamental feature of reality, present in some degree wherever there is integrated information processing, and that the particular form of consciousness you experience is a function of the mathematical structure of the information integration happening in your brain. On this view, consciousness is not produced by the brain, it is instantiated by the mathematical relationships in the brain, and those mathematical relationships exist in simpler forms everywhere in the universe. Electrons don't have thoughts, but they might have some infinitesimal degree of experience, some minimal form of interiority, because they are systems that have information structure. If you find this unsettling, you are reacting correctly, because it means that the division between the experiential and the physical, between mind and matter, between the observer and the observed, is not where we thought it was. It might not be a division at all. There is a moment in the history of every scientific revolution when the pieces of the new picture come into focus with enough clarity that the inadequacy of the old picture becomes suddenly and starkly visible. Thomas Kuhn wrote about these moments as paradigm shifts, transitions from one conceptual framework to another, triggered by the accumulation of anomalies that the old framework cannot accommodate. And the paradigm shift is never comfortable. It requires giving up not just specific theories but entire ways of thinking about the world, entire vocabularies of concepts, entire habits of interpretation. The Copernican revolution required giving up the intuition that the Earth is at rest at the center of the cosmos, an intuition so deeply embedded in human experience that resisting it required enormous intellectual courage. The Newtonian revolution required accepting that the force that pulls an apple to the ground is the same force that holds the moon in its orbit, a unification so counterintuitive that it seemed almost mystical. The quantum revolution required accepting that particles don't have definite properties before measurement, that the act of observation influences the physical outcome, that the universe at small scales behaves in ways that are fundamentally incompatible with any classical mechanical picture. Each of these revolutions required abandoning assumptions that felt, to the people who held them, as obvious and inviolable as the floor under their feet. And we are describing a situation in which the next revolution, whatever it is, may require abandoning assumptions that feel even more basic, assumptions not about the motions of planets or the behavior of atoms, but about the nature of space, time, matter, causation, and experience themselves. Consider the following constellation of facts, not as separate problems, but as a unified message from the universe about the limits of our current understanding. Space is not fundamental. It emerges from quantum entanglement. Time is not fundamental. It is absent from the Wheeler-DeWitt equation. Matter is not what we thought. 95% of it is something we cannot see, detect, or explain. The vacuum is not empty. It seethes with virtual particles and should, by rights, have an energy density 120 times larger than observed. The universe had a beginning that our physics cannot describe. The universe contains structure that should not have had time to form. The universe is expanding at a rate that two independent measurements disagree about with 5 sigma significance. Fundamental particles have masses that are finely tuned to values that permit the existence of complexity, with no explanation for why. Quantum systems are non-locally correlated across any distance. Information may or may not be conserved in black holes. Consciousness cannot be explained by any current physical theory, and the theory that connects it all, the theory of quantum gravity that unifies the very large and the very small, does not exist. When you lay all of those facts side by side, the question that suggests itself is not, which of these problems will be solved first? The question is, what kind of reality would generate all of these problems simultaneously? What kind of reality would appear from within to have laws that are both extraordinarily precise and repeatedly insufficient? What kind of reality would produce observers who are cognitively capable of discovering its laws, but consistently incapable of finding the foundations beneath those laws? What kind of reality would contain within it the exact right conditions for complexity to arise, for life to evolve, for consciousness to emerge, for the universe to become aware of itself through the instrument of intelligent creatures and yet remain ultimately opaque to those creatures' deepest investigations? These questions don't have clean answers, but the fact that they can be asked, and that the answers are not obvious, is itself a form of data. It tells us something about the kind of universe we are in, whether we are in a universe that is fundamentally knowable and we simply haven't finished knowing it, or a universe that is knowable up to a point and then becomes systematically inaccessible, or a universe that is knowable only from within certain frameworks and we happen to be in a framework that is reaching its limits. We cannot say for certain, but we can say with confidence that the evidence points away from the first option and toward one of the latter two. Let's go back to the galaxies, because there is something about them specifically that deserves a deeper engagement. The JWST findings about early galaxies are not just a cosmological puzzle. They are a test case for a more general question about whether the universe follows the rules we have assigned to it, or whether the rules are approximations that break down in ways we haven't anticipated. The Standard Model of Cosmology, Lambda CDM, makes specific predictions about the abundance and properties of galaxies at every epoch of cosmic history. Those predictions are based on well-understood physics, gravitational dynamics, gas physics, stellar evolution, feedback processes, and they have been tested and refined over decades against observations of the nearby and moderately distant universe. The model works beautifully for the universe as it exists today, and for the universe as it existed several billion years ago. But the JWST observations suggest that in the very early universe, the model fails. The galaxies are too big, too structured, too numerous. The model predicts a universe that builds up complexity slowly, hierarchically, from small to large. What JWST sees is a universe that, in some regions and at some epochs, appears to have leapt to complexity much faster than the model allows. The possible explanations for this failure fall into a few broad categories, and each one has deep implications. The first possibility is that the lambda CDM model is essentially correct, but needs refinement in the details of how early star formation and galaxy assembly work. Maybe the physics of gas cooling and star formation in the early universe was different from what we've assumed. Different metallicity, different radiation environment, different feedback mechanisms, and these differences allowed galaxies to build up their stellar populations faster. This would be a relatively conservative fix. Adjust some astrophysical processes within the existing framework, update the parameters, and recover agreement with the observations. Some researchers lean in this direction, but the problem is that the adjustments required seem, to many astrophysicists, to be unreasonably large. The discrepancies between the model and the observations are not small parameter mismatches. In some cases, they require star formation efficiencies and rates that seem physically implausible, given what we know about how stars form. The second possibility is that the dark matter model is wrong. Lambda CDM assumes that dark matter consists of cold, slow-moving particles that form structures hierarchically, small clumps first, then larger structures growing through mergers. This bottom-up structure formation is one of the model's core predictions, and it generally works well. But there are variants of dark matter, called warm dark matter or fuzzy dark matter, in which dark matter particles have slightly different properties that alter the structure formation history. Some of these variants might allow larger structures to form earlier, but again, the required modifications are constrained by many other observations, and it is not clear that any variant of dark matter can simultaneously fix the early galaxy problem and remain consistent with everything else we know. The dark matter model is not just a cosmological assumption, it is embedded in a vast network of observational constraints, and pulling on one thread tends to unravel others. The third possibility is the one that makes cosmologists most uncomfortable, that the lambda CDM framework itself is fundamentally incomplete in a way that cannot be patched. That's something about the large-scale structure of the universe, the way space expands, the way gravity behaves at cosmological scales, the nature of dark energy, the initial conditions of the Big Bang, is different from what the model assumes, and that this difference has consequences for how structure forms in the early universe that are only now becoming visible because we finally have a telescope powerful enough to see that far back in cosmic time. This possibility doesn't just require updating a parameter, it requires reconsidering the foundations, and reconsidering the foundations of a theory that has successfully described nearly every cosmological observation for decades is not something scientists do lightly, but the data increasingly seems to demand it. There is a particular irony in the fact that one of the greatest scientific instruments ever built, an instrument designed to confirm and extend our existing understanding of the universe, has instead become one of the most powerful generators of evidence that our existing understanding is insufficient. The James Webb Space Telescope was not built to find the impossible. It was built to see further, more clearly, more precisely than anything before it. And what it has found in doing exactly that is a universe that is not behaving according to the rules, not in a small, subtle, easily dismissed way, in a way that is visible in the data, clear in the analysis, and confirmed by independent teams of researchers. The universe, when examined with sufficient resolution and depth, reveals itself to be different from what we thought. And the implication of that is not just that we need a better theory of galaxy formation. It is that the universe, at the scale of its very earliest structures, operated by dynamics that our current physics cannot account for. And if it operated differently then, it might be operating differently now in ways that our measurements are not yet sensitive enough to detect. This brings us to a possibility that is rarely discussed in accessible science communication, but that has been seriously proposed by a small number of theoretical physicists. The possibility that the laws of physics themselves might not be constant across all of space and time. The laws of physics in our current framework are universal and eternal. The speed of light is the same everywhere in the universe at all times. The charge of the electron is the same in a distant galaxy as it is in a laboratory on Earth. The strength of gravity is the same in the early universe as it is today. These are foundational assumptions, so deeply embedded in our theoretical framework that they are rarely even stated explicitly. They are the background against which all of physics is done, but they are assumptions. And there are observations, including some controversial measurements of the fine structure constant, a dimensionless number that governs the strength of the electromagnetic interaction, that suggests it might have been slightly different in the distant past. The evidence is disputed and the scientific consensus remains that the laws of physics are constant, but the dispute itself is significant. The fact that we feel the need to test the constancy of the laws of physics, that the question is not obviously already answered, tells us something about the level of our uncertainty regarding even the most basic features of the universe. If the laws of physics were not constant, if they varied in space or changed over time, or differed in conditions very different from those in which they were measured, the implications would be staggering. It would mean that our theories, derived from observations made here and now, might not apply to the distant universe or the early universe. It would mean that the fundamental constants are not truly constant, but are instead values that have settled into their current state from some deeper, more dynamic process. It would mean that the universe has a kind of physics history, a narrative in which the rules themselves change, and we have only ever observed a brief snapshot of that narrative from our particular vantage point. It would undercut the very universality of physical law that makes science possible as a global, predictive enterprise. We would not just need a better theory. We would need a theory that includes the evolution of the theory itself, a kind of metaphysics that describes not just the behavior of matter and energy, but the behavior of the laws that govern matter and energy. This is, admittedly, a minority view, but the fact that it is taken seriously by some very capable physicists is itself a symptom of the depth of the current uncertainty. We have been moving, paragraph by paragraph, deeper into a particular kind of darkness, not the darkness of ignorance, which can be lit by learning, but the darkness of discovered limits, which is a different quality altogether. There is a kind of knowledge that expands the space of what you know while leaving the space of what you don't know roughly the same size. And there is a kind of knowledge that expands the space of what you know while simultaneously making the space of what you don't know larger, deeper, and more structurally important. The history of fundamental physics in the past century has been emphatically the second kind. Every major discovery has not just filled in gaps but opened new ones, not just answered questions but revealed that the answered questions were standing in front of deeper questions that the answers couldn't even begin to address. General relativity resolved the inadequacies of Newtonian gravity and opened the questions of dark energy, singularities, and quantum gravity. Quantum mechanics resolved the problems of atomic stability and spectral lines and opened the measurement problem, the non-locality of entanglement, and the cosmological constant problem. The Standard Model resolved the proliferation of hadrons in the mid-20th century and opened the hierarchy problem, the matter-antimatter asymmetry, and the nature of dark matter. Each layer of understanding has been genuine, each has been a real advance, and each has revealed that the universe is stranger, deeper, and less tractable than the previous understanding suggested. The matter-antimatter asymmetry deserves a moment of focused attention because it is another entry in our growing list of things that simply should not be the case. When the universe was created, when in that first unimaginably brief and hot moment matter and energy came into existence, the laws of physics as we understand them predict that matter and antimatter should have been created in exactly equal amounts. For every particle created, an antiparticle of equal mass and opposite charge should have been created alongside it. This is a consequence of the deep symmetries in the laws of physics, specifically the charge conjugation and parity symmetries, and it is robustly predicted by all known theories. If matter and antimatter were created in equal amounts, then as the universe cooled, matter and antimatter would have annihilated each other completely, leaving nothing but radiation, no atoms, no stars, no galaxies, no planets, no people, just light. The universe we live in, the universe of matter, of structure, of everything that exists, should not exist. It should have annihilated itself in the first second, and yet it didn't. Somehow, matter won. For every billion antiparticles that were created and annihilated, there was one extra particle of matter that survived, and from those survivors, everything was built. This asymmetry between matter and antimatter is called baryogenesis, and while we know that it happened, we are here, which proves it. We do not have a complete explanation for why it happened. The Standard Model of particle physics contains a small amount of what is called CP violation, a slight difference in the behavior of particles and antiparticles under certain conditions, and this CP violation in principle can drive a matter-antimatter asymmetry. But the amount of CP violation in the Standard Model is far too small to account for the observed asymmetry. The matter-antimatter imbalance that gave rise to everything we see is larger by many orders of magnitude than anything the Standard Model can produce. There must be additional sources of CP violation, additional physics beyond the Standard Model, that explain why matter 1. We don't know what that physics is. We don't have a confirmed theory of baryogenesis. The universe's most fundamental act of self-creation, the process by which it chose matter over antimatter, by which it chose to exist rather than annihilate, is something we cannot explain. The existence of anything at all, of you, of the planet beneath you, of the star that lights your sky, rests on a physical process that our best theories cannot account for. Let's pause here and let the weight of that settle. The existence of matter, not some exotic matter, not some rare form of matter, but all matter, every atom of every kind, depends on a slight asymmetry between matter and antimatter that our theories predict should not be as large as it is. The universe as a whole, not as a particular structure within the universe, but the universe as a whole, as a material entity, should not exist by the lights of our best physics, and it does exist. You are sitting here, made of atoms that should never have survived the early universe's matter-antimatter annihilation, in a body that is the product of a 4 billion year evolutionary process on a planet that should never have had the elements to form, orbiting a star that had the right mass and longevity because the fundamental constants were tuned to permit it, in a galaxy that is far too large and mature for when it formed, in a universe that is expanding at a rate our two best methods of measurement disagree about, filled with invisible dark matter that we cannot find and invisible dark energy that we cannot explain, structured at the quantum level by entanglement and superposition that undermine every classical intuition about locality and definiteness, and located in space-time whose geometry may be a holographic projection of a lower-dimensional informational substrate. You are the product of impossibility stacked upon impossibility, and somehow, impossibly, you are here. There is a concept in physics and mathematics called an attractor, a state or configuration toward which a system tends to evolve regardless of its initial conditions. The classic example is a pendulum. Wherever you start it, however high you raise it, however hard you push it, it will eventually settle into a specific pattern of motion determined by its physical properties and the influence of friction. In a more complex system, an attractor can be a complicated, fractal-like structure, what is called a strange attractor, that the system spirals toward without ever quite reaching a fixed state, tracing out intricate, non-repeating patterns that are nevertheless constrained to a specific region of the system's state space. Some physicists have speculated that the universe as a whole might be like this, a system that, regardless of its initial conditions, evolves toward states capable of hosting complexity, consciousness, and the kind of organized structure we observe. The universe, on this view, is not just accidentally suitable for life and complexity, it is in some sense attracted to those states, but an attractor is only meaningful if we understand the dynamics that generate it, if we can write down the equations that describe the system's evolution and identify the regions of state space toward which it tends, and we cannot do that for the universe. We do not have the equations, we do not have the framework, we do not have the conceptual vocabulary to even formulate the question properly. The speculation about cosmic attractors is beautiful and suggestive, but it is a gesture toward an understanding we do not possess, a pointing finger that indicates a direction without being able to describe what lies at the end of it. And that gap, between the gesture and the understanding, between the pointing and the destination, is where we have been living throughout this entire conversation. It is the gap between what we can observe and what we can explain, between what the universe shows us and what we can make sense of, between the data and the theory, between the anomaly and the framework. And the gap, as we have seen, is not small. It is not a narrow crack that a little more work will seal. It is a chasm that widens the more carefully you measure it. Consider for a moment the strangeness of your own position as the person experiencing this video. You are a collection of approximately 7 octillion atoms, that is a 7 followed by 27 zeros, arranged in a configuration of such extraordinary complexity that it gives rise to subjective experience, to the ability to ask questions about its own nature, to the sensation of curiosity and unease that you may be feeling right now. Those atoms obey quantum mechanical laws that we cannot interpret without controversy, interact through forces that are described by a standard model that we know is incomplete, are held together into the structure of a body by chemistry that rests on quantum foundations we cannot fully reconcile with the theory of gravity, on a planet that exists because fundamental constants were tuned to values that permit planetary chemistry, in a galaxy that is too large for when it formed, in a universe whose composition we understand only at the 5% level. You are a node in a web of mysteries, made of unsolved problems, sustained by unexplained constants, looking out at a cosmos that is 95% invisible and asking questions that have no answers. And the deepest, most unsettling thing about your position is not that you don't know the answers. It is that you are beginning to suspect that the questions themselves, the way you have been framing them, the categories you have been using, the assumptions you have been making about what kind of thing the universe is, may not be adequate to whatever the universe actually is. There is a moment in the history of cartography that feels relevant here. In the age of exploration, European maps of the world had a convention for regions that were unknown, regions that no European had yet traveled to and returned from. They would write there in the empty spaces the phrase, "Hic sunt dracones," here be dragons. It was not an assertion that dragons actually lived there. It was an acknowledgement of the limits of knowledge, a marking of the boundary beyond which the map gave way to pure uncertainty, beyond which the categories and knowledge of the cartographer were no longer reliable guides. We are, in the deepest regions of fundamental physics and cosmology, in the territory of Hic sunt dracones, not because we have stopped trying to map it, not because the tools of science are no longer being applied, but because the instruments we have sent into that territory, our mathematics, our experiments, our theoretical frameworks, keep coming back with reports that don't fit on any map we know how to draw. The territory is real. The instruments are working, the data is good. But the map-making system itself, the conceptual framework that converts data into understanding, seems to be reaching something like a boundary condition, a place where it can gesture but not grasp, describe but not explain, measure but not comprehend. And now we arrive at the place where all of these threads converge, not into an answer, but into a question of a particular quality and depth. Throughout this exploration, we have encountered anomalies that should not exist according to our best theories. Galaxies formed too early, dark matter that cannot be found, dark energy that defies calculation, a matter-antimatter asymmetry that our models cannot explain, quantum non-locality that undermines our concept of space, a vacuum that should be 10^120 times more energetic than observed, an arrow of time that has no fundamental basis in our equations, a moment of creation that our mathematics cannot describe, constants tuned to life-permitting values by unknown mechanisms, and a theory of consciousness that doesn't exist. We have explored possible explanations, new physics, extended frameworks, holographic principles, emergent spacetime, and found that each explanation, while illuminating in its domain, creates new questions faster than it answers old ones. We have traced the pattern of anomalies and found that it is not random, not evenly distributed, not the kind of pattern that suggests we are merely filling in the last few percent of a nearly complete understanding. It is a pattern that suggests something systematic, something foundational, something that goes all the way down. The scientists who discovered the early JWST galaxies went back to their data. They checked it again and again and again. They asked their colleagues to check it. They changed the instruments and ran the measurements a different way. And every time the galaxies were there, sitting in an era of the universe where they had no right to be, staring back at the instruments with a kind of quiet defiance. They shouldn't exist. The universe, as we understand it, does not permit them. And yet there they are. And there is dark matter everywhere in the rotation curves of galaxies and the gravitational lensing maps, nowhere in any detector. And there is dark energy, filling every cubic centimeter of space with its mysterious repulsive pressure, carrying no identity, offering no explanation. And there is the quantum vacuum, seething with virtual particles that should be screaming with energy, but are instead whispering politely, at exactly the level that allows the universe to persist. And there is the matter you are made of, which should have annihilated itself before it had the chance to become anything. And there is the consciousness with which you are reading these words, which no physical theory can fully account for, which feels like the most certain thing in the universe, more certain than any measurement, more certain than any equation, and which remains at the level of fundamental physics a complete mystery. Something that shouldn't exist does exist. Many things that shouldn't exist do exist. The universe itself, in a very precise and well-documented sense, should not exist, and yet here it is, in all its staggering complexity and scale and beauty and mystery, persisting in the face of every theoretical objection, violating every expectation, containing within it billions of galaxies, each of billions of stars, each potentially hosting worlds, and on at least one of those worlds, creatures who have spent centuries trying to understand how all of this is possible. And those creatures, Those scientists, those physicists, those cosmologists pointing their telescopes at the darkness and their instruments at the quantum void have found with increasing precision and increasing alarm that the universe is not cooperating with the understanding, that it is not converging toward a final theory, that every layer of understanding reveals a deeper layer of mystery, that the map is not merely incomplete but may be the wrong kind of map for the territory it is trying to describe. And tonight, in laboratories and observatories and theoretical physics departments around the world, people are looking at the data and feeling something that science rarely acknowledges but that every scientist has felt. Not just the excitement of discovery, but the vertigo of genuine incomprehension. The sensation of standing at the edge of something immeasurably vast, with instruments that were never designed for what they have found, in a universe that continues to be, in its deepest nature, entirely unknown. And so the question that remains, the question that cannot be answered here, that cannot be answered anywhere right now, that may not be answerable by any mind that evolved on the surface of this small planet, orbiting an unremarkable star in the outer regions of one of those impossibly ancient and impossibly massive galaxies, is not, what is the explanation? The question is something stranger and more fundamental than that. It is the question of whether the thing that shouldn't exist, the anomaly, the violation, the impossible galaxy, the invisible matter, the inexplicable energy, the tuned constants, the non-local entanglement, the timeless quantum vacuum, the conscious observer who cannot explain their own consciousness, whether all of these things that should not exist are pointing not toward a gap in our knowledge, but toward a gap in our knowability, whether the universe is not merely unknown, but in some deep and possibly permanent sense, unknowable by the kinds of minds it has produced. And if that is true, if the universe has generated through the long blind process of cosmic and biological evolution, creatures sophisticated enough to ask the right questions, but not quite sophisticated enough to understand the answers, then what you are feeling right now, this particular quality of unease, this specific texture of not quite grasping, this sensation of reaching towards something that retreats as you approach it, is not a failure of understanding. It is understanding, arriving at its own horizon and finding that the horizon does not resolve into a further view. It simply continues to be a horizon. Ahead of it, something exists that we found, something that, by every account, should not be there. And we do not know what it means, we do not know what it is, we do not know if we ever will.